Hello, my name is Mitch Trainer, and today I'll be talking about the permanent magnet DC motor design. In this report, we'll be going over the motor design, the application for the motor designed, the parts list, the design strategy, and the risk analysis. When designing this motor, we decided to keep the radius of the motor around about 40 millimeters to ensure that it can be mounted in any kind of application. For calculations, the motor has been designed to incorporate an 8-pole simplex lap wound motor that will have 40 turns of wire per coil. This will result in 41 meters of cable at 19 AWG. The insulation on the cable will be 180 degree rated. This will probably be polyurethane or polyurethane nylon to ensure a safe operation at a higher current for a long period of time. When considering between lap wound or wave wound, we decided to go lap wound as it is better for low voltage and high current applications. The decision to be running at 12 volts was mostly because we want to be accessible to a lot of applications, and the most common battery would be a car battery. To work on the calculations, we needed to make some assumptions. The assumptions we made was that it would be a simplex winding, 8-pole motor, lap wound, 18 to 29 AWG motor winding cable, a maximum cable length of 45 meters, a flux leakage of 50%, a degradation factor of 20%. We were limited to 5 different magnets: the 2522, 3495, 3460, 3470, and the LM1614. With the LM1614, after simulations, we decided that this magnet was not strong enough and was not worth testing. For the expected results, we went through an Excel spreadsheet and inserted all of our assumptions and our low-level calculations. This ended up giving us our K1 and K2 values, and also all of the other maximum torque and other values. As we had a look into our motor design, we decided to do a simulation. To start the simulations, we did a torque first time. As you can see, the 3495 magnet is the strongest magnet initially, but tapers off the fastest. Then followed by the 2552 magnet, then the 3470 magnet, then the 3460 magnet. This makes us think that for a more reliable motor, it's going to be the black or the blue that'll come through. The back EMF versus time corresponds fairly well with the velocity versus time. As we can see, the light green magnet 3495 is again the first and follows the same sequence. For current versus time, we can see that the first 3 magnets are quite close together, though the blue magnet 3460 it holds a fair bit more current for a bit longer and then tapers away at the same rate. For angular acceleration, we notice that the light blue 3495 magnet has exceptional acceleration to start with and gets to max speed exceptionally quick. The red magnet 2552 is a little bit slower and is comparable with the black magnet 3470. The blue magnet 3460 gives the calmest amount of acceleration, which is probably what we're looking for in our design. As we look at the velocity versus time, we notice that the green and the red, so the 3495 and the 2552 magnets, don't actually make it to our desired 1000 RPM. So that leaves those two out of the equation. As the black magnet 3470 does make it past 1000 RPMs. It only just makes it past there. So it will be comfortable at getting to it, but holding there is going to be quite hard for the magnet. As we can see, the blue magnet 3460, it manages to get almost up to 1600 RPMs. This means that that magnet will probably be able to, in the real world, get to the 1000 RPM measure. To continue our simulations, we decided to check the power and efficiency as speed increases. As we can see from the first magnet, it doesn't actually end up making it to the 1000 RPM mark. This is the same with the second magnet. The third magnet is the higher accelerating one that will make it up to almost 1600 revs per minute, which means if you look up at the line from the 1000 mark, its efficiency is quite high at around about 14%. With the fourth magnet in the motor, we see that it does make it to 1000 RPMs, though because it's after its steep cutoff period, it only makes it to 6% efficiency. This motor has been designed with the electric wheelchair in mind. Even though the electric wheelchair is our main focus in this design, our motor should still be compatible with an electric skateboard or electric scooter, or even something like a kayak motor, as these things require nice even acceleration and a consistent top speed. The parts list for this motor includes a commutator, some brushes that will fit the commutator, a DC power supply, if that's a battery or a power supply, 41.08 19 gauge wire, a 3460 magnet, a shaft for the motor, a ball bearing ring to hold the shaft steady, an epoxy to seal the windings once wound, and some form of mechanical protection. The design strategy of this motor includes a step-by-step of how to build the motor. Step 1, get all components. Step 2, once the cable has been completed, insulation test and test resistance as per specs and change the design if needed. 3, build the motor internals, which means getting the laminations in order and placed correctly, putting the commutator on the shaft, ensuring the brushes are placed properly with the commutator, the test resistance across the brushes. Build the frame and hold the motor once wound. Start winding the motor in a lap wound system. When you're winding the motor, try and lay the cable in as flat as and make levels if appropriate. Once the winding is complete, we need to test the insulation to make sure there's no shorts and ohm test each individual wind, because we need to make sure that they're even as possible anyway. Then you place the magnets in the correct place and test the polarity of the magnets. Then you assemble the motor components to make a test situation, and then test by momentarily activating to ensure it will actually rotate. If all pass, then the motor is ready for a test run. If the test run passes, the motor is ready to go. As we were designing this motor, we decided it was the best idea to do a risk analysis so everyone can go to work and then go home safely at the end of the day. When we're testing in the lab, we'll most likely have to use a heat gun, which can do some small burns and irritation, but is very likely. So what we need to do is wear some heat-proof PPE to reduce that risk. The insulation tester can give a small shock and a bit of a start, can't really do too much damage, though we should still wear PPE about it. The rotational pinch and wrapping of the rotor when it's spinning is a very big risk. It's not super likely, but if it does happen, it can be very severe. So what we have decided is to barricade any spinning object and wear PPE and limit any kind of loose clothing or hair being done. Overcurrent heat, it's not a really big deal. We just need to put a current limiter in there. In the real world motor, there'll be different things that we can look at later. Thank you for listening to my speech, and have a good day.